far below the productive surface. A cold water coral polyp adds an almost imperceptible layer to its skeleton. Years pass above, while the colony's living edge advances by increments too small for a diver to notice. This slow construction introduces a deeper question. Why does growth often proceed cautiously in the deep ocean? Darkness itself does not stop growth, but it removes photosynthesis and changes how energy reaches consumers. Most deep habitats depend on food produced elsewhere, delivered as sinking particles, carcasses, migrants, or currents. That delivery is irregular, diluted across immense volumes, and frequently consumed before reaching the bottom. Cold temperatures can further slow biochemical reactions. Although temperature alone never explains every deep-sea life history, high pressure changes molecular and cellular conditions, but adapted organisms function successfully within their normal depth ranges. The central engine is an energy budget constrained by sparse meals and expensive maintenance. Every new gram of tissue competes with movement, repair, reproduction, and survival through the next lean interval. Slow growth becomes understandable when waiting is common, and replacement food cannot be predicted. Yet the deep sea contains many environments, including productive canyons, oxygen-poor margins, vents, and whale falls. Creatures there do not share one universal pace, and some grow rapidly when resources arrive. The investigation, therefore, follows carbon downward, asking where energy is lost and how survivors allocate what remains. Our opening coral records the answer slowly, but its skeletal archive also preserves environmental change. Sunlit plankton fix carbon near the surface, beginning much of the food supply for deeper waters. When organisms die or produce waste, particles descend as marine snow through a crowded water column. Bacteria and animals consume, fragment, and transform that material during its journey. Only a fraction of surface production reaches abyssal depths, with the proportion varying by region and season. Large, fast-sinking particles can deliver brief pulses that contrast with long periods of scarcity. Seafloor time-lapse observations document animals responding quickly when fresh detritus arrives. The cue is a food fall. The action is feeding or aggregation, and the consequence is temporary energy gain. After the pulse, activity may decline as consumers return to conserving limited reserves. Metabolism describes the chemical work sustaining cells, and its rate is influenced by temperature, size, activity, and ecology. Many deep-sea animals exhibit low metabolic rates compared with active relatives from brighter, food-rich waters. This pattern is especially associated with low food supply and reduced need for continuous, high-speed swimming. However, powerful deep predators and vertical migrants show that depth does not require universal sluggishness. Cold water can reduce reaction rates, but evolutionary adaptation modifies enzymes, membranes, and physiological performance. If you lifted a deep animal rapidly, decompression and warming could obscure its natural metabolic state. Reliable comparisons, therefore, require careful handling or measurements made near ambient conditions. Growth occurs only after assimilated energy covers essential maintenance and losses. When meals are small or widely separated, allocating energy slowly can extend survival between opportunities. Long lifespans often accompany slow growth, delayed maturity, and infrequent reproduction in stable, deep habitats. These traits form a life history pattern, not a rule applying to every species below a chosen depth. The Greenland shark, Somniosus microcephalus, provides a striking vertebrate example of slow growth and exceptional longevity. Age estimates from eye-lens radiocarbon dating carry uncertainty, but they support a lifespan measured in centuries. Its cold environment, large body, and low apparent growth rate fit an unusually slow life history. The evidence does not isolate one cause, so no single factor should be declared responsible. Deep-sea corals reveal slow tissue and skeletal accumulation through repeated measurements and dated growth structures. Some colonies may persist for centuries, turning small annual gains into large three-dimensional habitats. Their polyps capture suspended particles and plankton carried by currents rather than relying on sunlight. Current speed can raise food delivery, but excessive flow or sediment may interfere with feeding. The cue is passing prey. Tentacles capture it, and the consequence is energy for maintenance and incremental construction. Periods without suitable particles force the colony to live on stored resources and reduced expenditure. Radiometric dating and repeated imagery provide complementary evidence across different spans of time. Dates can span uncertainty ranges, and images can miss subtle tissue changes. Agreement among methods strengthens conclusions without making growth histories perfectly precise. Sponges offer another window because many deep species build bodies through slow filtration of scarce suspended food. Pumping water costs energy, so filtration must yield more usable carbon than the process consumes. Some sponges host microbial partners that help transform dissolved or particulate compounds. Those associations expand possible food pathways, but they do not create energy from nothing. Stable cold conditions can reward durable tissues that function for years rather than rapid replacement. Low predation or disturbance in some settings may also reduce the advantage of fast maturation. Where disturbance is frequent, however, slow growers can be removed faster than populations recover. Growth estimates must separate actual tissue addition from changes in posture, water content, or seasonal feeding. For gelatinous animals, apparent size can be a poor measure of accumulated organic material. For mineralized animals, skeletal extension may continue while tissue condition or reproductive output changes. Deep growth is therefore multidimensional, involving length, mass, skeleton, maturity, and stored energy. An animal may add little length while investing substantially in repair, reserves, or developing reproductive tissue. The most informative studies specify which component was measured and over what interval. Oxygen availability adds another constraint because cells need suitable electron acceptors for efficient aerobic metabolism. Oxygen minimum zones can compress habitats and alter feeding, movement, and community composition. Some residents possess adaptations that sustain function at low oxygen, often with behavioral or physiological trade-offs. Tolerance permits survival, but does not automatically produce rapid growth under limited food. Pressure increases steadily with depth and affects protein stability, membranes, and biochemical equilibria. Deep organisms possess molecular adaptations, including pressure-compatible cellular chemistry, that keep essential processes operating. These adaptations explain survival under pressure more directly than they explain a particular growth rate. You should therefore picture pressure as part of the operating environment, not a universal brake pedal. The energy budget explanation becomes clearest when an unusual feast reaches the seafloor. A whale carcass can concentrate enormous resources in a landscape normally supplied by scattered particles. Mobile scavengers arrive, consume soft tissue, and support a succession of organisms using remaining fats and bones. Some populations grow and reproduce faster during this temporary abundance, demonstrating that food can release constraints. Hydrothermal vents similarly support high local productivity through chemosynthesis rather than sunlight. Vent tube worms can grow rapidly compared with many background deep-sea animals because microbial partners access rich chemical energy. Their pace disproves the idea that darkness or pressure alone forces slow growth. Instead, the contrast between vents and surrounding plains isolates energy supply as a dominant variable. Temperature, oxygen, predation, and evolutionary history then modify how that energy becomes tissue. Slow growth has serious consequences when humans disturb deep communities. Bottom contact fishing can remove corals in moments after structures accumulated over centuries. Mining tests and proposals raise concern because sediment disturbance may outpace recovery in extremely slow-growing communities. Recovery estimates remain uncertain where baseline ages, recruitment rates, and connectivity are poorly known. Caution follows from the asymmetry between rapid damage and potentially prolonged rebuilding. Climate-driven changes in surface productivity could alter the amount and timing of carbon reaching depth. Ocean warming also changes oxygen distribution and metabolic demand, producing effects that may pull in opposite directions. Long records are required to distinguish natural pulses from persistent shifts. If you revisit the coral, a single photograph cannot reveal whether its edge is growing or merely surviving. Future evidence needs repeated, calibrated images across years without repeatedly damaging the colony. Chemical tracers can estimate food sources, while dated structures can constrain longer growth histories. In situ respiration measurements may connect energy use with temperature and food delivery. No method alone captures feeding, maintenance, skeletal extension, and reproduction across an entire lifespan. Researchers must also study fast-growing exceptions because they test which supposed constraints are truly necessary. Comparisons across vents, slopes, canyons, and abyssal plains can separate depth from food supply. Monitoring after natural food pulses can show how quickly stored energy becomes tissue or gametes. Juvenile recruitment must be measured separately because adult persistence can conceal decades of reproductive failure. Comparisons among related species may reveal adaptations associated with longevity, but ancestry alone cannot measure growth in nature. You can expect future estimates to retain uncertainty, especially for animals older than the observing programs. That uncertainty should widen age ranges, not erase the consistent evidence for remarkably slow lives. The strongest explanation remains conditional. Scarce usable energy often favors conservation, delayed investment, and gradual construction. Where energy becomes abundant, some deep creatures abandon that pace, exposing the limits of any simple rule. Our coral's next skeletal layer will be thin because survival receives the first claim on an unpredictable deep-sea budget.